So we are going to start the steam power plant. Okay, so what are the basic components of the steam power plant? First of all, there will be a pump. Okay, pump, boiler, turbine, condenser. First of all, let's talk about the boiler. Okay, boiler is a generally is a device. Okay, constant pressure device in which the hot combustion gases will be due to how combustion process. It will increase the temperature of the boiler. Constant pressure heat addition process. Okay, it will increase the temperature of the steam, high pressure and high temperature. Generally, if you look at the boilers are maintained at high pressure. Why high pressure? Because requirement of latent heat is very less. Latent heat, why we are maintaining boilers at high pressure? Generally, latent heat is used to, that energy is used to convert the liquid to directly steam, right? Liquid to directly to the steam. So when we at high pressures, that latent heat requirement will be very less. So it will be converted into steam very fast. So therefore we are going to use a high pressure boiler. Now how high pressure is maintained in the boilers? So generally we are going to use the pump. Okay, pump is the main device which is used to increase the pressure from 1 bar to 150. Suppose for example pressure will be less than 1 bar, right? Suppose say 1 bar, 1 bar to 150 bar, 150 bar inlet pressure will be P1 will be equal to 150 bar. So constant pressure heat addition, the steam, what liquid will be converted into steam. So that steam is sent to the turbine to expand. Okay, turbine, that device which expands, right? So from there low pressure and low temperature steam is present. So we need to condense that steam, right? So we are going to use a condenser. So condenser cooling water is used to condense that steam. Okay, so same water is same liquid we are circulating, right? The same liquid we are circulating to the cooling towers. All right, same water will enter powers in which the evaporative cooling will take place, and same it will send to the pump, and this cycle repeats. All right, so generally the turbine, at the exit of the turbine, we are getting low pressure and low temperature steam, right? So the question arises that why we are using the condenser. Before going through this question, first of all, what is the advantages of the power plant? When you look at the advantage of the power plant, then one of the advantages is efficiency is high, and the any type of fuel can be used. Okay, low quality of fuel can be used. Suppose coal can be used. Okay, wood can be used. But what are the major limitations of the power plant? Size is the major limitation of the power plant. The size will be very good, very big. So why the size is big? Why the power plant is very heavy? Because of the condenser. Okay, when you look at the condenser area which is taken by the condenser will be very high, and condenser will be heavy. And cool for for cooling water, to circulate the cooling water we need a cooling tower, right? So cooling tower, once you look at the cooling tower, the size of the cooling tower, it is very big, right? So area and it weight wise, the the power plant will be very big because of the size of the condenser. And boiler size is very big, but when compared to condenser it is very little bit small. Okay, so why we are using the condenser? What is the use of the condenser? What is the essential use of the condenser? Why can't we directly at the output of the turbine there is low pressure and low temperature steam, right? So why can't we directly feed it to the boiler? We can't feed it to the pump. Why we can't feed it to the pump? Because because pump is a low pressure device, right? We can't feed steam to the pump. Okay, instead we can use a compressor. But before using the compressor, I can tell you that what if we directly feed it to the boiler? So first of all, when we look at the boilers, is already steam is present, right? So when we supply the steam, then latent heat requirement will be less. Q will be less, right? Latent heat requirement will be less, so Q decreases. So why can't we use it? So why can't we directly compress it to the again we can use a compressor to increase the pressure and temperature. And why can't we use the compressor in the middle, and why can't we feed it? Okay, compressor work will be more than pump work, and network output for the pump compressor increases, and heat net heat also decreases na. So why we are using the condenser in the middle? So why can't we use the compressor? Okay, even though net heat input is decreasing, network input is increasing, but net heat, actually the cycle is not possible. According to, it is a violation of second law of thermodynamics. The system is not possible actually. Without rejecting heat, it is not possible. Okay, like suppose for example, compressor work will be greater than the turbine work. Okay, instead of generating electricity, or you need to supply the work from the compressor. Okay, you need to supply an electrical energy for compressor to work. Okay, so generally at the exit of the turbine there will be low pressure and low temperature streams, right? And the volume will be very very less. The volume will be very very more. Okay, V will be more. So compressed, the volume will be very very less, right? So dp you need to create. So therefore if you look at the dp, you need to create dp. So you need to supply more work for the compressor. Okay, you will get less work from the turbine. So therefore instead of getting the electricity, you will so you will supply the electricity. Okay, so second case, if you supply the fresh water, what happens? All right, so generally when you look at the case number 2, if we what if we supply the fresh water instead of taking the same water from the condenser. So we can supply the fresh water, but there are certain limitations when you supply the fresh water. First of all, when you talk about the steam, once you talk about the steam, okay, steam, uh, suppose for example lake, I am taking the water from the lake, because the water requirement will be very very more, right? 90 kg per second, 90 kg per 100 kg per second. Okay, 1000 tons of water is required, so I must go through the closer to the river. Okay, once I go closer to the river, then I will circulate the water from there. But generally whatever the water is coming, whatever the steam is coming from the generally the pressure of the water, pressure will be atmospheric pressure, right? And in the turbine the pressure will be more. Okay, it will not expand. So what will be the temperature of steam? Temperature of the steam will be 100, somewhere around 100 degrees centigrade. Okay, so actually pressure will be more. Okay, pressure will be more, but if the steam is at 100 degrees centigrade, then it has got lot of energy. That lot of energy we are unnecessarily are wasting, right? We are wasting that energy. So that is one thing. So if you use a condenser instead of wasting that energy, condenser temperature will be nearly 10 to 15 kPa, not MPa. 15 to 10 to 15 kPa. So it can expand that pressure. It can expand. The turbine will expand more. So we will get more work output from the turbine. So efficiency will increase. All right. So therefore we are using the condenser. But the second case, in the second case, one of the disadvantages is also, we need lot of water, right? We need lot of water, and we are not going to use the normal water. We are going to use the chemically treated water. Okay, chemically treated water. So in the NTPC there is a plan, right? Water treatment department. There is one department, water treatment department. Okay, which they will chemically treat the water. Okay, for 1 liter nearly 6 to 7 rupees will be there. Okay, so how many kgs of water is required? 90 kg per second. Per second, that much kg of water is required. So price will increase, right? If you talk about normal distillery plant, it will be 0.5 liter per paisa per liter. Okay, the treatment cost will be very very more. So therefore we can't treat the water, new water we can't treat, and we can't waste the water, right? Also there, due to the pollution, we can't directly fill the water in the river. Okay, so therefore the condenser. Why the condenser must be needed? What if you use a compressor work output will be more when compared to turbine, right? And work input will be more when compared to turbine work output. So efficiency will decrease. Will work, but system is not possible according to second law. That tells that heat must be rejected. Okay, that is the thing. And if you use the fresh water, there will be two disadvantages. One, treatment cost will be more, and second, in the first case, in the case one, advantage one, then the maximum amount of heat will be wastage. Okay, so therefore the condenser is necessary. Okay, so generally now we are going to discuss about the vapor power cycles. In the vapor cycles, working fluid changes its phase during the cycle. Okay, so generally when you look at the first cycle, ideal vapor power cycle, that is Carnot vapor power cycle. In the power cycle, the fluid is changing its phase. Okay, so generally it will be saturated liquid, then we are changing the phase, we are making it to the steam, then again we are making it to the fluid, and this cycle is repeated. Okay, so generally when you look at the four processes in the Carnot cycle, first of all is adiabatic compression, exothermal expansion, adiabatic expansion, isothermal compression. Okay, so why can't four process will be isothermal compression? Okay, does the reversible adiabatic expansion compression expansion possible? Yes, it is possible. Okay, we are ideally we are taking, but in the vapor power cycle, auto cycle, diesel cycle, adiabatic process is possible. Okay, reversible adiabatic process is possible actually, but why can't we replace adiabatic with isothermal process? That is the main thing he didn't told. Okay, so generally when we look at it is possible when in a multi-phase system, it is not possible in a single phase system. Okay, so generally if I take the process, imaginary process from 1 to 2. Okay, suppose if I take the saturated liquid at point 1. Okay, now what I am going to do, I'm going to supply q in at constant temperature. At constant temperature when I am supplying, that means there is a change of phase, right? There is a change of phase. It means that is a two phase system. So there is a change of phase in the sense temperature will be constant. I should add only latent heat, right? So temperature will be constant, so there is no problem here. Okay, now when I want to when I look at the when I take the second imaginary process, that is 2 to 3, here there is only single phase. Now it is not possible to add it. Okay, if you add it, there will be no phase change. If there is no phase change, then it is a single phase, right? Single phase system. So here we can't achieve isothermal process. It is very difficult to achieve the isothermal process because you can't change the phase. Okay, so that is the thing. So that therefore first process is reversible adiabatic compression process. So second process is isothermal expansion, that is heat addition process. Then reversible adiabatic compression process, and isothermal compression, that is heat rejection process. Okay, these are the four processes. Now how to calculate the TL and DH value? As you know, efficiency is 1 minus TL by DH, right? So how to calculate TL by DH value? You can calculate TL at PL at constant pressure, right? Adiabatic P at PL, I am going to sorry, there will be pH and PL, right? There will be pH and PL. So what will be TL? TL is T saturated at PL and T saturated at pH. Okay, this you need to know. Okay, so 1 minus TL by TH equal to W by Q input. How to calculate Q input? Q input can be calculated, we learned in the properties of pure substance, right? So HF HG, there will be HG minus HF gives you Q in, right? H3, enthalpy at H3 minus enthalpy at H2, enthalpy at H3 minus enthalpy at H2 gives you the Q in. So how to calculate enthalpy at HT? You just to take pH, then you will get enthalpy at H3. At pH, Hg value gives you enthalpy at H3, and at pH, HF value will give you enthalpy at H2. Okay, here we are not writing Hg and HF, but generally we are making some changes, right? We are taking the points. Okay, we are considering the points H2, H3, H1, H4, or like that. Okay, so from there we are going to calculate the enthalpy values. Okay, once we calculate the enthalpy values, then it will be easy for you to calculate the work done. Okay, this chapter is very simple, just to remember the things. Okay, just revise and remember the things. Alright, so generally when we look when we look at the 3 points, 3 drawbacks. Okay, why not Carnot? Okay, so actually when you see the 4 processes, reversible adiabatic isothermal process, expansion, adiabatic reversible adiabatic expansion, and isothermal expansion compression, you may say that a reversible adiabatic process is not possible. Isothermal compression expansion, it is possible, but reversible adiabatic process is not possible. So we can say that. Okay, so actually if we replace adiabatic with reversible, it is reversible adiabatic is possible. Why can't so you just replace reversible adiabatic like auto cycle, diesel cycle, they are adiabatic process, right? So why can't you use the Carnot cycle? Okay, so generally when you look at the first point, when you look at the condensation, there is a partial condensation is taking place. Okay, so it is difficult to design and control a device. Okay, it is difficult to design a device and to control the device which is doing the partial condensation. Okay, it is difficult to design the partial condenser and to control this partial condenser. It is difficult. Okay, so when you look at the when you look at the when you look at the exit conditions, there is a liquid plus vapor, there is a liquid, also there is vapor, because there is a partial condensation, right? So to increase the pressure of the liquid, you are going to use a pump. To increase the pressure of the vapor, what you are going to use? You are going to use a compressor, right? So it is difficult to design a device, it is difficult to design a device which increases the pressure of the mixture actually. So it is not possible, it is difficult. Okay, so therefore this is the second drawback. And the third drawback, when you see the adiabatic expansion that is taking place in the turbine, when you look at the quality of the steam, it is taking inside the vapor dome, right? So when you look at the quality of the steam, is decreased, quality of the steam is very less, therefore it creates a wear and tear in the turbine. So so these are the three drawbacks by which we are not going to use a Carnot vapor power cycle. Okay, but when we talk about the closed system, there in the second law we discussed one Carnot cycle, right? Same cycle, but there was a ideal gas. Okay, there is not, isothermal is very slow process and adiabatic is very fast process. One is slow, one is fast, so therefore that is not possible. Okay, that is a cycle which gives the maximum efficiency, right? So next we are going to talk about the work ratio. The ratio of net work output to the positive turbine work is given by work ratio. So generally when we look at the work ratio of Rankine is greater than W net of Rankine is greater than the W net of Carnot, and work done by the turbine is equal to the work done by the turbine in the Carnot. Okay, so work ratio of the Rankine is greater than the work ratio of the Carnot. This is one of the important statement. Okay, actually, so in generally when we are selecting a power plant, work ratio, we will not select the power plant based upon the efficiency. Okay, work ratio is our main concern. So suppose if work ratio is very high, that means it is a good power plant. Okay, so work ratio of the Rankine cycle is highest among all the power plants because of the pump. Generally the pump we are using, that is a VDP work, right? So volume will be very less because it deals with the liquids. Okay, so pump work is very small. So suppose for example work done by the turbine is 1000, work done by the pump is 8 to 10. So work done by the turbine is nearly equal to W net. Okay, so nearly equal to W net. So that means work ratio nearly equal to 1. Whereas in the gas power plant, the work ratio is nearly 0.4 to 0.6 because the compressor work will utilize the maximum amount of turbine work. The Rankine cycle is like 0.9 to 0.98. So after work ratio, we are going to talk about the back work ratio. Back work ratio is defined as a ratio of negative work to the positive turbine work. Negative work to the positive turbine work. Okay, so backward ratio for Rankine cycle, W net for Rankine cycle is greater than wait, W turbine of Rankine cycle equal to W turbine of compressor, right? Carnot cycle. So W pump work for the turbine for the Rankine cycle is less than the compressor work for the Carnot cycle. So W net of Blackwood ratio, we can say that Rankine cycle for Rankine cycle is less than the Carnot cycle. So generally after a certain manipulation we can get WR plus BWR equal to 1. Okay, so backward ratio must be as low as possible. Okay, work ratio must be as high as possible. Alright, so next we are going to discuss the specific fuel consumption, steam consumption. It is defined as a mass flow rate of the steam required to produce unit power. Okay, mass flow rate of the steam required to produce unit power. Okay, generally in the boiler we are converting steam and the steam is expanded in the turbine to get power output, right? So what is the mass of the steam which is required to get the unit power output is known as specific fuel consumption. It is given by the mass flow rate of the steam divided by power output, okay, to get unit power output, right? Specific steam consumption. So ms by power output we can write as ms into w net, okay, ms into w net. W net, units of w net, just look, units of w net is kilojoule per kg, okay. W net, that is specific work, network output, network, specific network, okay. So SSC is given by 1 by W net, kg per kilojoule. So convert kg per kilowatt hour. We are dividing with 3600. Okay, SSC will be equal to 3600 divided by W net. So as we can see that SSC is inversely proportional to W net, right? So W net of the Rankine is greater than W net of compressor, right? W net of Rankine is greater than the W net of compressor Carnot. So therefore specific steam consumption of Rankine is very less when compared to specific steam consumption of Carnot, because W net is more. Alright. W net of the Rankine is greater than W net of the Carnot. Okay, SSC, specific fuel consumption for Rankine is less than the specific steam consumption of Carnot. Okay. Actually, it is used to denote the size of the plant. If SSC is specific steam consumption is very large, then size of the power plant which is required, produce the power less. SSC is very large, then to produce unit power more large steam is required, so plant's capacity will increase. Okay, alright, that is the context of SSC, but in the problems we'll look ki kya hai iska significance and how to solve the problems based upon this. Okay, until and unless you can't solve the problems on the specific concept, you can't get into the कि concept से असल questions कैसे पूछे जाते हैं, what the basic idea, concept तो समझ में आता है, but the concept का जो मज़ा है वो है problem solving करने में. Okay, when you solve the problem based upon this concept, then you will come to know that okay, I applied the concept right. Alright, so next we are going to analyze the simple Rankine cycle. So now we are going to analyze a simple Rankine cycle. Okay, so generally when we look at the diagram, if you take the point 1, point 2, so actually the cycle is working between the two pressures, right? First one is condenser pressure at point 1 and second one is boiler pressure. Okay, so generally a point 1, as you can see, it is on the saturated liquid line. Okay, so generally point can be on left hand side and right hand side. Point can't be at right hand side because generally there is a liquid plus vapor is present. Okay, generally liquid plus vapor is present, and pump is used only to increase the pressure of liquids, right? So we cannot use for vapors. So even a little bit of uh, vapor is not required. So therefore point 1 is starting from saturated liquid. Why can't it be left hand side? Because we need to supply more energy. Why unnecessarily supplying more energy? Okay, therefore we will be take saturated liquid actually. Okay, all right. So if we for 1 to 2, it is a reversible adiabatic increase in pressure in the pump. Okay, reversible adiabatic it means almost isentropic. Okay, almost isentropic. So entropy will be constant, and almost it is isentropic, but it is slant line, I don't know. But after this completion of this unit, we will analyze that thing. Okay, so constant volume process. Next, it is a constant volume process. Now we are increasing pressure to the boiler pressure. Once we increase the pressure to the boiler pressure, now we are supplying the heat. Sensible heat, latent heat, and sensible heat. Okay, from 2 to 3. And again we are expanding, right? A reversible adiabatic expansion process. About point 4 can't be on the saturated vapor line. Why? Because we discussed it, right? Saturated vapor line, it can't be on the saturated vapor line. Okay, because it has more potential, right? It has the temperature and pressure, when you notice, it is less than the greater than the condenser pressure. So we are going to lose the potential. Okay, we are going to extract the maximum amount of heat from the in the turbine, right? So we are again expanding to the condenser pressure. So in the condenser the pressure is very less, so So we'll utilize that potential. Okay, so generally one problem is that you generally said that you can ask the question that you said that if the if you are going to increase, that drainage fraction is going to decrease, right? If drainage fraction going to decrease, then there will be wear and tear in the turbine. There will be liquid droplets will present. So why we are expanding till the condenser pressure? The point is on point is on in between liquid plus vapor, right? There will be drainage fraction, there will be amount of liquid droplets will present. But generally when you look x equal to 9.95, 0.96, this is a good quality of steam actually. So there will be liquid droplets which will be present, of course that will be present, but they are very smooth fine particles. Okay, so they will not create that much wear and tear in the turbine. So that is not the big problem. Okay, for the drainage fraction to be 0. But we must make sure that drainage fraction must be in between 0.95 greater than 0.90. Okay, the drainage fraction is greater than 0.90, then we are considering it as a good quality of fuel. Okay, generally in the gas power cycles our aim was to find out the temperatures, right? But in the vapor power cycle our aim is to find out the enthalpies. Okay, so now we discuss about the each and every point. Okay, and now we are going to now we are going to calculate the enthalpies at each and every point. So now our job is to find out the enthalpies. So let's just consider the process 1 to 2. So how to find the enthalpy at 1? Enthalpy at 1 will be equal to enthalpy of the fluid at condenser pressure. Alright. So for how to find the enthalpy at pump? So enthalpy at point to find can be found out by using the first law, right? H1 plus Q equal to H2 plus W. Q will be 0 because adiabatic, and H1 plus Q equal to H2 plus W. H2 will be equal to H1. So W we are considering negative, right? H1 plus W. WP of the can calculate by using first law. Apply the first law for the pump. WP will go VDP 1 to 2 VDP. Okay. So 2 to 3 is a constant pressure heat addition process. So how to find the enthalpy at point 3? That is H3 at H T sub and P sub. Pressure boiler pressure and T sub. How to find the enthalpy at point Q in at point 3? Q in. So H3 H2 plus Q equal to H3 plus W. So W will be 0. Alright, because constant pressure, right? So we'll get Qn equal to H3 minus H2, right? 3 to 4 reversible adiabatic expansion in the turbine. So how to find generally when you look at enthalpy at 4, how to find the enthalpy at 4? And the point 4 is at in between the vapor dome, right? So liquid vapor is also present. So drainage fraction तो आता ही आता है इसमें, क्योंकि drainage fraction एक ऐसा ये है which defines the system at this point. Okay, so S3 equal to S sub at pH T sub. So S3 will be equal to S4. S4 क्या है? S5 SF plus X4 SG minus SF equal to S3. SF FG SF ये क्या है? ये जनरली PL पे फाइंड आउट कर सकते हैं. इट इज एट PL. Now H4 equal to HF plus X4 HG minus HF. So from there we are going to calculate X4 drainage fraction at 0.4, and we are going to substitute here. At PL we are going to find out the enthalpy of fluid and enthalpy of gas and enthalpy of fluid. So from here we'll come to know that HF4 equal to H4 can. So if we apply turbine first law in the turbine, H3 plus Q equal to H4 plus W, we can calculate H3 minus H4. W net equal to W turbine minus W pump work. Efficiency we can calculate specific fuel consumption, steam consumption we can calculate. We can calculate power. Okay, we can calculate mass flow rate. Okay, again when you want to find out the QR, we just apply the equation. QR equal to H4 minus H1. So if we ask mass flow rate of water or change in temperature of water, cold water, that is T2 minus T1, and you can simply apply the energy balance in the condenser. Heat lost by the hot steam will be equal to heat gain by the cold water. MSH4 minus H1 equal to MWCW T2 minus T1. Okay, this was the concept of simple. And now we are going to discuss one problem. Okay, we will calculate But before going to a problem, let me revise the properties of pure substance. Alright, so now we are going to discuss about the methods to improve the performance of the Rankine cycle. Okay, right. So first case we are going to discuss. Okay, so in the case number one, when you look, we can increase the boiler pressure. What happens when you increase the boiler pressure? We are going to discuss those things. Okay, so generally when we are increasing the boiler pressures, to increase the boiler pressures, what we have to make the changes. Okay, we have to change the pump. Okay, size of the pump will increase, size of the pump will become large. Okay, so and we are taking care that we are not going beyond T superheated. Okay, we are not going beyond T superheated. Okay, so generally what happens to a turbine work, what happens to enthalpies, q in each and everything we are going to discuss. First of all, let's discuss about the h3. What happens to h3? H3 will increase or decrease. Okay, h3 is going to decrease. Why? Because generally if you are increasing the boiler pressure, corresponding temperature will decrease, and the heat required will be decreasing, right? So enthalpy will decrease, of course. So enthalpy will decrease. Okay, h3 dash will be less than h3. What about h4? H4 will increase or decrease. Generally when you look, h4 can be calculated at PL, right? So we can't say that at PL h4 will be constant. Okay, h4 hf and hg will be constant, but generally dryness fraction is going to decrease. Once the dryness fraction is going to decrease, then h4 dash is going to decrease. H4 dash will be less than h4. Okay, h4 dash will be less than h4. Now come to the turbine work. Turbine work is given by h3 dash minus h4 dash. Generally h3 dash is decreasing and h4 dash is decreasing, right? h4 is decreasing, so h4 is decreasing by more amount. Why h4 is decreasing? Generally when you look, h3 dash and h3 and h3 dash we calculated. Okay, what is the difference between h3 and h3? Are nearly 30. So generally when we if the fraction is decreasing by 0.1 only itself, then 150 there is decrease in h4 is 150 units. Okay, so when we talk about the 0.01 dryness fraction itself, it is decreasing by 30, so h4 will dominate h3. Okay, so turbine work is going to increase. What about pump work? Pump work is going to increase, but it is remains same. So generally he told one tip to calculate the pump work. Generally pump work, at he will give the pressures. Okay, he will give the lower pressure and he will give higher pressure. Generally pump work will be equal to the higher pressure. If you have less times for 7 MPa, pump work will be equal to 7 kilojoule. Okay, if it is 8, then pump work will be equal to 8 kilojoule. Okay, generally pump work is not going to differ. So what about net is W turbine minus W pump, and W turbine will dominate, so W net is going to increase. Okay, W net is going to increase. Once the W net is going to increase, then what happens to the Q in? Q in is going to decrease. Why? Because generally h3 value is decreasing, as q in is given by h3 minus h2. So h2 will be nearly equal. h2 dash will be nearly same. What are the nearly same values? h2 dash are nearly same values, and pump work is nearly same value. Okay, so q in is going to decrease. Q in is going to efficiency equal to W net increase W net by Q input. Q input is decreasing, W net is increasing, it means efficiency will, of course, it will increase. Whatever specific steam consumption will decrease, because we are less amount of steam is required to create the unit power, right? Unit power output. So steam input is decreasing, so specific steam consumption is decreasing. Quality of the steam at the exit is decreasing. So generally now question arises that if we increase the boiler pressure, then we are getting positive results, right? W net is going to increase, W turbine is going to increase, W pump and each and everything, Q input is going to decrease, efficiency is going to increase, each and every benefit we are getting. But question arises that how much we can increase. Okay, if you are talking about the boiler pressure, increment of the boiler pressure, how much we shall increase? All right, how much we shall increase? So generally we can increase the boiler pressure by it depends upon the x. Okay, x, and generally x decide how much pressure we can increase. So generally you need to take care about the x. If you don't take care about the x will create wear and tear. Okay, ये लास्ट में जोक मारा था मगर ज़बरदस्त था वो, ठीक है. And yeah, X, and he told that I tells you to how to handle X. All right, ठीक है चलो. Okay, so next is decrease in the condenser pressure. Okay, so generally we are going to decrease the condenser pressure. Okay, so when we decrease the condenser pressure, what happens to the turbine work? Turbine work is going to increase. Okay, because it is going to expand. Turbine is going to expand, right? Expand more, expand to low temperature. So Q in will also increase. Pump work will be same, but efficiency. What about efficiency? We can't say by this formula. We can say by mean temperature of heat addition is going to decrease, right? And mean temperature of heat rejection is also going to decrease. But heat rejection, mean temperature of heat rejection is going to decrease more than decrease in the mean temperature of heat addition. So therefore efficiency will increase. Specific steam consumption is going to decrease. Quality of the steam is going to decrease. Now how to decide generally what should be your condenser pressure? So generally if the steam is coming at 25 degrees centigrade, your steam temperature is condenser temperature is 30 degrees centigrade. Okay, so generally if it is 30 degrees centigrade, then you can't reject the heat. How steam will not reject the heat. So therefore condenser pressure must be decided by cooling water temperature. Okay, so corresponding saturation temperature must be greater than the cooling water temperature. Okay, it must be less than 25, 20, 15, 10 and like that. Okay. Suppose for example if you say that in the Jammu and Kashmir I am preparing the plant, water at the Jammu and Kashmir is 5 degrees centigrade, condenser pressure corresponding pressure will be nearly 2 kPa, 3 kPa. Okay, what happens then generally? Efficiency going to increase or decrease? Efficiency will increase, but the major problem occurs is that generally there is a chance of leakage. Due to pressure difference. The liquid will not leak outside, because outside temperature is 100 kPa, inside temperature is 2 to 3 kPa, right? So therefore air will leak inside the condenser. How it will leak? Through the pump. If it leaks through the pump will start working. If pump stop working, boiler stop working, तो whole plant will stop working. जनरली यहाँ पे जोक मारा था ना, राहुल गांधी को बोलो कि कंडेंसर में एक छोटा सा होल डाले. अब जाके कंडेंसर में नहीं, बॉयलर में होल डाले. Alright, so yeah, next is superheating. Alright, we discussed till decrease in the condenser pressure, I think. Yes. So next we are going to discuss about the superheating. Okay. So if we superheat, generally what happens, the drainage fraction is going to increase. Okay. मैं छाला या बात करने भी यहाँ. Drainage fraction is going to increase. So what about work done by the turbine? Work done by the turbine is going to increase. Pump work will be same. Q in will increase. So work mean temperature of heat addition is going to increase. Therefore efficiency will increase. Okay. Generally important है. Generally to design the first to design what we are doing, ideally we are designing and we are improving. Okay, so generally one tells you to design the Rankine cycle, okay, power plant, then you should ask him at what temperature the steam is available. Okay, suppose the steam is available at 30 degrees centigrade, 32 degrees centigrade. So steam is expanding, right? So steam is traveling, so temperature will increase. Actually, let's say 40, 45. Okay, 45 is right. What is the condenser pressure respect to condenser saturation condenser pressure with respect to 45? That is 9 points. And so 10 is chosen. Okay, so 10 is chosen saturation pressure. So asking what is maximum temperature actually. Maximum temperature, he will tell you that it is 400 degrees centigrade. Okay, old 4 to 450 is used, new 55, 60 to 600 is used. Now the efficiency is decided. Okay. Now efficiency is decided. Now what you will do, you will value boiler pressure. Now what you will do, your efficiency now tells you to improve the efficiency. Now how to improve the efficiency? Generally, to increase the maximum, why you can't increase because of metallurgical conditions. Okay, that boiler is designed, material is designed for that much temperature itself. Okay, so now can't increase the temperature. So next you increase the condenser pressure, decrease the condenser pressure. You can't decrease the condenser pressure because saturation temperature is same. Cooling water is available at 30 degrees centigrade. So next one option is left to, that is the boiler pressure, increment of the boiler pressure. So if you increase the boiler pressure, then dynastics fraction is going to decrease. There will be a problem in dynastics fraction. Then what you will do? So there is one solution to get the benefit of high boiler pressure. There is only one solution. That what we are doing, we are increasing the boiler pressure and we are expanding the steam. Okay, there is partial expansion of the steam. Again, we are reheating and we are expanding in the second turbine. Okay. So that is the concept of reheat. Okay. Right. So yesterday we studied till reheating, right? So comparison of reheat cycle with simple Rankine cycle. Okay. So the cycle, the efficiency of cycle may decrease or may increase depending upon the main effective pressure, right? So generally, in the steam power, if the steam expands more in first turbine or in case one, then you know mean temperature of heat addition is going to decrease and the efficiency is also going to decrease. So in most of the practical cases, steam is expanding slightly in the first turbine and then mean temperature of heat addition increases. Mean temperature of heat addition is increasing and efficiency is increasing. Due to reheating, quality of the steam at the exit of the turbine is increasing. All right. So next, regeneration in the Rankine cycle. The main aim of the regeneration is to increase the efficiency of the cycle by increasing the mean temperature of heat addition. Okay, generally he explained this regeneration in the Rankine cycle, but generally as I tell you that there is sudden discussion in this topic. So first of all, we talked about a simple Rankine cycle, right? So simple after the discussion of the simple Rankine cycle and reheat cycle, regeneration is going to be an important topic. Okay, so after the boiler, what we are doing, we are suppose for example 1 kg of the steam is entering, 1 kg of water is at high pressure is entering the boiler, and that water is converted into steam in the boiler is constant pressure, right? So 1 kg of steam is leaving from the boiler and entering the high pressure turbine. Now suppose for example 5 MPa of the steam or 7 MPa megapascal of the steam, right? So it is going to expand in the high pressure turbine. So when it's expand in the high pressure turbine, we are extracting the y kg of steam from the high pressure turbine. Now remaining steam 1 minus y kg of turbine is going to the low pressure turbine, and from the low pressure turbine 1 minus y kg of steam is going to expand, and that is going to in the inlet of the condenser. 1 minus 5 kg of steam from the condenser, kg of water from the condenser. It is now generally when we look the in the feed water heater, 5 kg of steam is 5 kg of water is entering in the feed water, right? So generally we are condensing the steam here itself. We are removing the steam in the condensed state. We are removing the steam in the condensed state. That means the liquid state. Whatever the latent heat which is present, latent heat will be lost by this high pressure steam, right? Whatever the high steam which is lost, whatever the heat energy which is lost is gained by the water.
Water will increase its sensible heat. Okay, water is going to increase its sensible heat by absorbing the latent heat from the steam. All right, so there is a feed water heater. So generally when you look the why the pump P1 is used. So when you look at feed water heater, the pressure is more, right? Pressure is more. Okay, so the pressure is actually the pressure is more, so we want a pressure in the condenser is very less. So from condenser to if we want to pump it into feed water heater, the one pump is required, so that is a pump P1. And next, from feed water heater to boiler, but generally if we need another pump, right? To in boiler the pressure is very large. Okay, to pump that feed water heater to the boiler, and we need pump too. Okay, so this is the cycle when we discuss about the TS plot. Okay, so 1 to 2, 1 to 2, what is 1 to 2, sir? 1 to 2 is actually the pump. Okay, a reverse adiabatic increase in the pressure in the pump, right? So when the pressure is increasing, is an isentropic process. Okay, temperature will increase. Now 2 to 3, what is 2 to 3? 2 to 3, as you notice here, key generally from process 5 to 6, you just notice 5 to 6. 5 to 6 is the adiabatic high pressure turbine, adiabatic expansion of that steam in the high pressure turbine, right? So 6 to 3, when you notice, this is the latent heat actually. Latent heat losing, the steam is losing its latent heat. Okay, steam is rejecting its latent heat. That energy is utilized from 2 to 3. Okay, 2 to 3 is the increase in the temperature. 2 to 3 is the increase in the temperature. By absorbing the latent heat, sensible heat of the water is going to increase. And 3 to 4 is again the 3 to 4 is again the increase in the pressure, right? Temperature will also increase. Uh, and 4 to 5, when you talk about 4 to 5, when you talk about 4 to 5, 4 to 5 is again heat addition in the boiler. Okay, 5 to 6. And 7 to 1, 7 to 1 is again 7 to 1 is we are using the condenser, so not to get more expansion. Okay, to utilize that energy in the turbine. Okay, so this is all about the regeneration cycle. Generally we are here, the important component is feed water heater or bleeding, we can say. Okay, जनरली द वाटर को जो ये होता, तो दैट वी कैन से वाटर ट्रीटमेंट जो रहता उसको वी कैन से दैट एक टेक्निकल टर्म है वो. ओके, this is all about the regeneration cycle. Generally we are feeding, suppose the temperature, the water of the temperature of the water which is feeded to the boiler increases, then latent heat requirement increases, right? Decreases. Once the latent heat requirement, it requires less amount of q in, right, to increase the temperature. So therefore the efficiency is going to increase. All right,